Welcome to this explainer. Today, we're diving straight into the terrifying mechanics of Himalayan cloudbursts and the really incredible scientific detective work used to reconstruct them. We're going to explore exactly how these massive storms form, why they're so lethal, and how researchers piece together the aftermath when the very instruments meant to record the data are completely washed away. Let's kick things off with a staggering number: 100 millimeters of rain per hour. To put that into perspective, imagine dumping a fully loaded bathtub over a tiny patch of land continuously for an hour straight. It is a truly massive amount of water falling from the sky. And that intense volume right there, 100 millimeters an hour, is the defining threshold of a cloudburst. We're talking about a sudden, violently aggressive rainstorm that unleashes an absolute wall of water over a really small area in just a matter of minutes. This isn't just a heavy rain shower, it is a fiercely concentrated deluge. But how exactly are these monster storms born in the first place? Section 1. The cloudburst phenomenon. The anatomy of a storm. So the whole process is essentially a violent chain reaction. First up, you have warm, moist air being forced up the steep mountain slopes. As this humid air rises into the higher altitudes, it forms these massive clouds. But here's the catch. Because there's a real lack of upper air at those heights to blow the storm along and dissipate it, the cloud basically gets trapped. The water concentration just keeps building and building until it can't hold on anymore, and it suddenly dumps all of its water at once. When you see the complete mechanism laid out step by step, you really get a sense of how the steep mountain terrain actively works against the environment here. The slopes force the moisture up and trap it, and then, because there's often little to no vegetation to absorb the impact or slow the water down, a devastating flash flood is practically guaranteed. Section 2. The Himalayan tsunami, a trail of destruction. Now, there is a specific geographic hotbed for all this vulnerability, known as Zone 7, which covers the western Himalayan states like Uttarakhand, Himachal Pradesh, and Jammu and Kashmir. Because communities here are so often nestled deeply into these steep, narrow valleys, the destructive power of these highly localized storms is magnified exponentially. And the historical toll here is just relentless. Back in 2004, the Alaknanda River abruptly swelled, sweeping away vehicles and leaving 17 dead. In 2010, the Leh disaster completely wiped out nearly 2,000 homes. Then came the 2013 Kedarnath event, which is grimly referred to as the tsunami of Himalaya, taking over 10,000 lives. And in 2014, Kashmir was struck again. These aren't just statistics, right? They are repeated, catastrophic tragedies for the people living there. Section 3. The data dilemma. The missing evidence. So, this brings us to a massive central mystery. How exactly do you prepare for or measure a flood when the sheer extreme violence of the water totally destroys and washes away the very instruments meant to record it? Scientists actually call this the ungauged dilemma. Because cloudbursts are so hyper-concentrated, usually hitting an area no bigger than 20 to 30 square kilometers, and they're over so quickly, traditional monitoring just flat out fails. The ground monitoring in these remote areas is already poor, and the literal force of the boulder-strewn water destroys whatever physical gauges might actually be there. So researchers are forced to rely on things like floodwater scars on stream banks, uprooted trees, and the harrowing testimonies of eyewitnesses just to piece the event together. Section 4. Reconstructing the flood, the mathematical detectives. Since the physical gauges are gone, hydrologists have to play mathematical detectives. Older basic methods, like the empirical or rational formulas, consistently underestimate the sheer volume of these extreme events. So researchers have to turn to advanced synthetic unit hydrographs. These are essentially mathematical simulations of how a specific volume of water flows over time, using methods like Snyder's and the SES to get a highly accurate virtual picture of what actually happened. When you pit these mathematical tools against each other, the difference is totally stark. The older, rational method trails way, way behind the much higher and faster peaks predicted by the advanced Snyder's and SCS models. And those massive higher peaks? They represent the sudden, violent rush of water that those local eyewitnesses actually reported. To give you an idea of the stakes here, let's look at the actual data reconstructed from that 2010 Leh cloudburst. By adjusting the mathematical parameters specifically for the steep, barren mountain terrain, researchers found that Snyder's method nailed it. It accurately reconstructed a terrifying peak flow of over 120 cubic meters per second. Now contrast that with the older formula, which guessed a mere 5.5 cubic meters per second. That is a massive and potentially fatal miscalculation. And the resulting steep, narrow curve from Snyder's method is wild. It isn't just a line on a chart, it literally represents a fast-moving, massive wall of water that hits its absolute peak in under 20 minutes. It offers virtually zero warning to any of the villages downstream.
Section 5. Preparing for the future. Future-proofing the mountains.
Because we now know how to mathematically reconstruct these unrecorded events using methods like Snyder's, the absolute most urgent next step is building a comprehensive database across the entire Himalayan range. Think about it. We simply cannot manage a disaster we don't understand. For the millions of people living in these valleys, this robust data is the literal foundation of life-saving disaster management. Which leaves us with one final, really urgent thought to take away from all this. Researchers point out that climate change, alongside increased human activity in the region, is actively aggravating these phenomena. So as our climate changes and these localized storms grow even worse, are our predictive models and our data readiness going to be enough to save lives the next time the mountains unleash a cloudburst?